Thank you very much. It's a great pleasure to be again in Moscow, and I would like to thank the organizers for giving me this opportunity to talk. My talk is based on a joint work with Murat Kalaglu, Peter Kravchuk, and David Simmons-Duffin. We just finished two very long papers, quite technical, and the topic is conformal bootstrap and holography. But since, as far as I know, not many people here are working on this, so please ask questions and let's keep it more informal so that at least you can follow a little bit. So let me start with some introduction. And I will be interested in this talk in quantum field theories in flat space. And when I say quantum field theory, I guess everyone has his favorite definition. For me, quantum field theory will be, say, for this talk, a set of correlation functions which satisfy Weitman axioms. Haack-Kastler axioms doesn't matter, but it will be the usual things that we assume. Plus, on top of this, I assume that there is a stress tensor, a conserved spin-2 current. And usually in these axiomatic formulations of quantum field theory, this is not a part of the axioms. But I will assume that the stress tensor exists because if we have a stress tensor, we can measure energy. And measuring energy is good. Yes, please. Oh, yes. Everything is gauge invariant at any point. It's a gauge invariant operator. Sorry? Well, that's what quantum field theory is. It's a set of local operators. So I'm talking about quantum field theory. Yes. I assume existence of a quantum field theory. I assume existence of stress tensor, which is gauge invariant and conserved. So if we have a gauge invariant conserved stress tensor, we can measure energy density. And of course, measuring energy density is very important, especially in the context of gravity, because well, that's the meaning of Einstein equations, only provided we know something about the right-hand side. And there is this beautiful fact about quantum field theories that the energy density in quantum field theories can be negative. Or stating more precisely, the theorem goes as there are no positive local operators in quantum field theory. And the way you prove it, you can prove it, you say, assume that you have a positive definite local operator. Say I smeared it here. Now construct this two matrix with omega be in vacuum and sign be in some state. And if it's a positive definite operator, this matrix has to be positive semi-definite. So you compute the determinant, and because the vacuum of quantum field theory is Poincare invariant, this matrix element is 0. So the only contribution to the determinant comes from this diagonal, which is an absolute value. So minus absolute value has to be positive. The only solution to this is that this matrix element is 0. So we just proved that if this operator is positive, then its matrix element with any state is 0. That set of states, we can choose a complete set of states. So we conclude that local operator smeared with some f with a contact support, and then the Risch-Leiter theorem tells you that that's not allowed. So QFT vacuum, it's known as a QFT vacuum is separating, which is that if omega is a vacuum state, and psi is any state you like. So whatever you like.
So what do you assume that vacuum is
yes, exactly, yes. Because vacuum is Poincare invariant, has 0 momentum, 0 charge, and so, yeah. Okay, fine, that's a known fact. But of course, if we want to make sense of Einstein equations, we want to assume something, and in particular, all the famous results, or many famous results in general relativity, the big part of it is in energy conditions, strong, weak, dominant. But we just proved that in quantum field theory, we do not have such local conditions. So what's going on? And of course, the resolution of this puzzle is that in quantum field theories, we do have non-local energy conditions. And one energy condition which I will be talking about is known as an average null energy condition, which is a statement that, let's say, we take a flat space, we take a stress energy tensor, we choose light cone coordinates, x plus minus, we integrate over a complete light ray, and the statement that this operator is positive. This result was proven in any quantum field theory recently in these two very different looking papers, and that's one of the interesting features of this result is that in this paper by Faulkner, Lay, Parikar, and Wong, they use sort of information theoretic methods. And in the paper by Hartman, Kundu, and Tajdini, they use the bootstrap methods to prove the same result. And it's very hard to make, well, it's not.
Question.
Yes?
In the second paper of Hartman, do they do it for generic theory or just for conformal?
Yeah, they do it for CFTs, but I think then if you add QFT, if you think of quantum field theory as a CFT with a flow, then the only things that they use, they take a pair of operators to create a stress tensor, and I think this part is not sensitive to the RG flow because they go close to the light cone. And I would say that maybe there are some subtleties which you know about, but I would say that the proof is for QFT as well because they use a very general axioms and then. Yeah.
Just in one or two words, what is your final goal?
Yes.
What do you want to show us?
Yes, so I would like to study, so I would like first to tell you a little bit that this is a very interesting and important operator for many different reasons. And so we have to understand, we can ask about the properties of its properties. And in my talk, and I will try to explain next what people did before, they were studying sort of one-point functions of this operator. And so in my talk, I will tell you about our work to study the two-point function of this operator. So that's a goal. And as I will try to explain, understanding a two-point functions of light ray operators requires new technology, and it have a couple of very physical applications, which I'll try to explain. That's a goal.
So in terms of energy density and
Yeah.
potential, it means epsilon plus p is larger than zero?
Integrated, yeah. If you have any state, non-equilibrium doesn't matter. If you
Integrated is okay, like
yes,
local
yes,
epsilon
exactly.
plus p
That's right, yes.
And
But
this statement is for quantum field
for quantum field theory,
But if I can have classical field theory,
No, no,
where
in
it's violated,
yes.
then quantum field theory
No. So the claim, and that's the claim is that if you can violate that the fact that this density is positive locally, but if you integrate over all times, then it has to be positive. That's a claim.
overall time?
Over all times. Over all times. Imagine it's like a collider experiment. You turn on the detector and you integrate from minus infinity to plus infinity. And sometimes you detect something negative, but overall it has to be positive. That's
It's like code.
yeah. It's this.
X, dx minus.
This is, I think it's fair to say that we can think of this coordinate as time. So we integrate over time, so it's a kind of null time, but still. And well, as I want to connect to some applications, okay, this is a general fact, but few applications of this condition that it's positive. It's one is that's related to causality and gravitational theories in the context of ADS-CFT especially, but also outside of it. And by this I mean that we have general relativity, it's effective field theory, we add higher derivative corrections, and we want to study what is the space of consistent effective theories of gravity. So this operator will be very important. And the second application, which I think I will talk a little bit more today, and I think we'll have a talk by Grigory Korchemsky on Friday. It describes event shape in a conformal collider experiment. So if you're a more gravitational person, you can think of propagation on trivial backgrounds. For the particle physicist, it will be more of collider physics. And as I said, there is this connection to information theoretic quantities. And there is also generalization of this energy-entropy relations, where you, instead of integrating over all times, you integrate over a finite period, and then this integral can be negative, and this is known as a QNEC. This is also discussed recently. So let me formulate what is a conformal collider experiment, and this is a setup for this thing called energy-energy correlator. It was first studied in the QCD in a plus and minus annihilation to hadrons. And for me, the relevant thing will be we consider a state created by a local operator. That would be the set of states. In the case of E plus, E minus, it's electromagnetic current. And then we let the particles, so whatever is created, to propagate, and we measure the energy flux at infinity. These detectors, these are energy calorimeters, and we run the experiment for infinite time. As I told you, that we integrate, so this is not a practical collider, it's eternal collider. And this connection that, in principle, you can do this using amplitudes, and that's what these people did in 85. But then it was understood that you can think of this in terms of operators and insertion of these ANEC operators. And it was first, as far as I understand this, realized in the paper from Moscow by Sveshnikov and Konchov in 95. They have an idea, then Korchemsky, Derder, and Sterman made it more precise, and we will hear a lot more about this by Grisha. And for me, the relevant part would be this paper by Hoffman-Maldacena from 2008. And what they did is that they considered this experiment with one detector. So we just have one detector, and the state is created by stress tensor itself. And they impose that this thing that has to be positive, and ask what is this, what kind of constraint is this? And why is it interesting is that, well, let me formulate, I wrote here the program of conformal bootstrap. In conformal bootstrap, you think of CFT. CFT is characterized by CFT data, set of anomalous dimensions, and set of 3-point couplings. And the goal is to carve the space of allowed values of couplings between particles or states. And so the idea is, the interesting part about this, as it happens very often in recent years, when you do Lorentzian experiments, when you study Lorentzian observables, we find some constraints which a priori we don't know how to prove in Euclidean, even though there are formal theorems like Osterwalder-Schroeder saying that it should be possible. In practice, it's almost never possible. And so what they found is that this constraint leads to non-trivial bounds on the 3-point couplings of stress tensor. Famously, 3-point couplings are fixed up to a set of few numbers. Yeah. Okay, very good. Let me define. So these are conformal anomalies in 4 dimensions. And in 4 dimensions, think of this. Let me take a CFT. In CFT, 3-point functions are fixed up to a set of numbers. This 3-point function of stress tensors contains in it 3 numbers. That's just a statement of the symmetry. A and C are certain combinations of these 3 numbers. And the claim is that you can derive this bound on them without, and there is no way to derive this bound. So it's a bound on the 3-point couplings of stress tensor. It's slightly imprecise. The actual, this is, usually people like it written in this form, so I wrote it that way, but the actual bound is just a statement that the 3-point function of stress tensors has certain positivity properties, which otherwise hard to prove. And there's, yes, and to connect to my title, this example, this integrated integral of a local operator of a light ray, it's an example of a light ray operator. That's what light ray stands for. And independently of Hoffman-Maldacena, it was realized around the same years that if you study Einstein gravity and you add corrections to it, high derivative corrections to it, and you want to impose causality of the theory, you also recover similar bounds. Actually, you recover precisely the same bounds from causality in ADS. And so this would be for me the 2 subjects, two physical problems that I will have in mind. One is event shapes in conformal collider. Imagine a strongly coupled theory. So we are studying event shapes in conformal collider. Or we have a gravitational theory, and we study high derivative corrections. So these are the problems.
Sorry, the same bounds over A equals C.
Sorry, so here you're right. So the claim is the following. So why is this A over C is nice is that if you have Einstein theory, you can compute 3-point coupling of stress tensors, and you get that A is equal to C in Einstein theory. You add a high derivative correction, A is not equal to C anymore. You get this alpha Gauss-Bernays measuring A minus C. You impose that the theory is causal. You recover these bounds. That's a claim. So now, coming back to your question, what is the goal of this talk? The goal of this talk is to consider a multi-point, and for simplicity, I consider 2-point functions of ANEC. Yes?
There's an non-trivial part here in this argument that you can consider only 2 derivative operators.
Yes, okay. It depends how precise you would like to make the argument. So it's true that in this paper by Brigante et al., they consider propagation on top of black holes, and this might be sensitive. But this argument by Hoffman, and that's the part of the shocks, it's a propagation of a graviton through a shock wave. And the argument of propagation of a graviton through a shock wave, it's insensitive to high derivative corrections. To be, again, more precise, it captures only the 3-point function of stress tensor. That's a more precise version of the story. Yeah. Okay, so I would like, yeah.
Could you explain why
Yes.
A squared term do not appear precisely in anti-de Sitter? A is equal to C, right?
Yes. So if we consider Einstein theory and we compute 3-point function, we get something, and for not known reason, at least to me, and I think to anyone, in terms of this conformal anomaly coefficients A and C, it's A equal to C. And it lies, of course, well within the window. So it's larger than 1/3 and less than. But I don't have a good answer to your question. Why is it 1? I think it's part of it is a convention. In a sense, you can redefine A or C. But yeah.
And in de Sitter, no.
So as you say, so the very interesting part of this program is, of course, the final goal is to constrain the theories in de Sitter and some cosmological theories. But the state of affairs is such that many methods which people are using and I'm using rely on the fact that there is a boundary so that I can discuss either correlators or S matrices. And one way people think about de Sitter in this subject, and you can agree with it or not, but the idea is that we start with a bounds, we derive an ADS of flat space, and then if these bounds seem to be sensitive to local physics, we can promote them on a bounds on effective field theories in de Sitter, but these are not really bounds, these are quasi-bounds, because we haven't proven them, but it's an educated guess of what is allowed. No. Okay, that's the state of affairs in de Sitter.
We see a simple explanation. If you just start with R,
Yeah.
you get trace anomaly which vanishes and reaches.
Yes.
And that happens only when you,
Yes.
balance.
Thank you. So the question is that what happens if we add two operators of this type? And you can imagine that it becomes much more non-trivial, even in collider experiment. If you create a SO3 symmetric state, 1-point function is fixed by symmetries, but 2-point function, if we have two energy calorimeters, we will see if there are jets in the theory, if there is non-trivial dependence. Or in gravitational theory, each of these operators will be dual or described by gravitational shock. So instead of propagating through a single shock, the probe particle will be propagating through a pair of shocks. And the goal would be to, well, one goal you might not care too much, it's to develop new computations with light ray operators and some strongly coupled theories. More practical goals is to derive bounds on corrections to GR, or to study event shapes and strongly coupled CFTs. So that's the goal.
You can claim that the GR consideration is as strong as just purely CFT.
GR, no, yeah.
Because what I want to do is at the level of GR.
So the way the logic goes is that, so we assume that we have a UV complete theory, or we have a complete QFT or CFT, which are basic axioms, and we derive a certain bounds. These bounds have to be obeyed in the consistent theories of gravity, which have some UV completion. Then we take the theories that you like. In GR, these bounds usually obey automatically. It's a very special theory which obey all the bounds. You now start adding to GR any other things on non-minimally coupled matter, and you will see that you can easily violate these bounds. So that's the game. That's the name of the game. Try to modify GR, and you see that it's not very easy.
Allowed modifications of GR.
Exactly, yes. The goal is, the final goal is to understand what are the allowed modifications of GR, and if you want to modify GR, what do you have to do? That's a big program, but here I will just say a few words about that. So. Okay, so let me tell you about light ray operators in conformal field theories, and this is slightly more general. And the idea is that, conformal field theory is divided in Minkowski space. So you take your local operator, integrate over light ray, so it goes from minus infinity to plus infinity. This is a Penrose diagram of Minkowski space. But as well known, you can take conformal field theories and continue them to the cylinder. And then it's on the cylinder, it looks like this geodesic that goes around once. So in this picture, it is clear that the light ray operator is labeled by starting point and a direction where it goes. So it's a null direction and the end point. Moreover, if you say start with a primary operator O and you do a light transform of it, that's a definition, you can convince yourself that you still get a primary. So if you live in the conformal world, this is a conformal operation. But this conformal primary has interesting quantum numbers. So if you start with a conformal primary with dimensions, say, delta and spin j, you get an operator which transforms like 1 minus j, 1 minus delta operator. And consistent with our first slide consideration, the general theorem about QFT, it annihilates the vacuum. So this is the general fact about light ray operators. They annihilate the vacuum. It follows from analytic properties of Whiteman functions. Now, why these light ray operators are very interesting? One reason is that they're closely related to a phenomenon which is of analyticity and spin, which occurs in quantum field theories, presumably in gravity also. And the statement is that usually when we have a spectrum of particles or a spectrum of local operators, it's labeled by discrete labels, which is spin 0, 1, 2, 3. But there are rigorous results. Recently, say, in old days as matrix, it was due to Froissart and Zhiboedov. And recently, it's due to Simon Caron, who basically proved that we should think of the spectrum as organized in terms of Regge trajectories. So the data is not just a set of random numbers, and this existence of Regge trajectories, which you can prove is closely related to the healthy high energy behavior of the theory. So that you don't want the amplitudes to grow too much, then you have to think about Regge trajectories. But then the construction of this analytic continuation of OPE data in spin you can do, and I will say something about it, but you can ask, what is this point? Okay, these points are local operators, spin 2, spin 4, spin 2, spin 4. What's some other random point on this, say, this point 3? What does it correspond to? And as explained in this paper by Peter Kravchuk and David Simmons-Duffin, we should think of this object as light ray operators. So from the point of view of this analyticity in spin phenomena is that light ray operators are very generic, and we should actually not think in terms of local operators, because if you can ask the question, okay, we have local operators in quantum field theory, can we analytically continue them in spin? And the answer is no, because if you try to do so, you will run into contradiction with Whiteman axioms. But if you try to analytically continue light rays, the statement is yes, it is possible. And that's what we can do. Therefore, we should understand in quantum field theory what happens on these trajectories, et cetera, et cetera. And so ENIAC operator is just an example of this.
So what happens to light ray when it crosses even something special?
Yeah. So what happens is that it becomes an integral of a local operator. In general, light ray operators cannot be written as an integral of a local operator. When this trajectory crosses this point, you can write a light ray operator as an integral of a local operator. Now, how do you do the computations with such exotic objects? And the answer is this CFT general. So, yeah. Yes, so these are objects which you can define non-perturbatively, but they are light ray operators, so they are localized on a null ray. You cannot write them in terms of fields, but you compute their matrix elements. I cannot give you a better answer to this. It's not integral of anything. You can, yeah.
Just as we defined in the beginning, it's light ray.
Yeah. Yes. Exactly. Yes. So let me just say in practice how do you do computation with this object. So, and the idea is this Lorentzian inversion formula, which is you do the conformal Fourier. So you start with a 4-point function, for example. And the statement is that you can do its Fourier transform, conformal Fourier transform, which is known as a partial wave, and Kolya talked about it a little bit. And then, as he explained, when you have some kernel here and you have complete base of functions, and when you close the contour, this C coefficients, they have poles, and these poles are nothing but the spectrum of your theory. Now, this kind of expressions that he wrote, and people wrote, for example, in the 70s by Dobrev, Mak, Petkov, Petrova, and Todorov, they only make sense for integer spin, but via manipulations which are very reminiscent, like dispersion relations, you can put these coefficients in a form which is manifestly analytic in spin. So the only thing which is sort of not very subtle is this -1 to the j. I will talk about it. But the point is that you can define these functions at any spin just because they have a representation which is analytic in spin, and it's given in terms of something known in the literature as double disk, which is a very Lorentzian object. You take a 4-point function and you compute a double commutator. So the point of the slide is that you can start with this integer spin expansion of it's for the amplitude it's partial wave expansion, or for the conformal correlator, and you can continue it in spin.
Is the group theory behind this
Yes, I think behind this one, so this one is as far as I know, it's part of this harmonic analysis and conformal groups, and this is I guess known as what's this name of the formula? It has a name. So this formula. Yes, it's a Plancherel formula. Yes. Yes. Yes, exactly. It's quantized here.
The question is when you relax this condition,
Yes.
what's the group structure?
Right. I don't know, but I think also one important thing is that it's not always, it should not be always possible to do this thing. So in going from here to here, it's important that this object, which we started with, is a physical correlator, and it has certain bounds like a Regge bound. So, and the analog of this group theoretically, I don't know. So I think it's a very interesting question, but I really don't have anything to say about it.
One feature of that group structure should not act in points in space, because
Yes.
it should be only
Yes.
modified on light rays.
That's right. Yes.
Some kind of twisted group.
There is also an interesting thing which is not understood in the literature, that this is a Plancherel formula for Euclidean conformal group. So there is a principal series only for delta, but for the Lorentzian conformal group, there is a similar formula, but with two Casimirs, and no one knows what is good for and how to use it. It's an open problem in the field to understand the role in life of the analogous formula for Lorentzian.
So we could ask,
Yeah.
so if you take n equals 4 and twist 3 operators, the number of states increases when you increase the spin,
Yeah.
not just one state per spin. So how do you not continue?
Yeah. So I think that's a question which is often asked. My understanding is that this always goes through, but then what can happen is that if you have this operator which seems to appear at certain twist, if you analytically continue, you will just have its residues being 0. So you will not see it at low spin, because this function is analytic in spin, but it has extra zeros, and then it has sort of appear because it's not 0 anymore.
So there is one continuation, which is
There-
zeros and one.
There is a one continuation, and then
So do you know which one is that when it was 4? Which states are connected to this?
well, sometimes it's easier to answer, sometimes I don't know. It's hard. I don't know. With twist 2, I guess we all know, but yeah. I'm starting worrying about time. Oh, wow. So I have 20 minutes. Okay. So that's how you define these light ray operators. You take a pair of local operators, integrate it with a kernel, and the kernel is dictated by group theory behind. It's basically partial wave expansion, which you weak rotate, and then light transform. And then by the same argument, you started with something meromorphic. You get that this object is meromorphic in delta I, j, and the light ray operator is defined as a residue of this transform. So it's defined indirectly. It's not in terms of fields. You start with the local operators. You do the kernel, and then you zoom on the residue. That's how you. And this plus minus, it's what's known as a signature. As a signature of an operator, I will explain this fact. It's also ancient fact that if you analytically continue in spin, you can continue independently from even spins and from odd spins. And this is a label in the Regge theory, which inherited also in the CFT. So one thing which I will first quickly discuss is that we would like, so I told you light rays are labeled by points in a null ray. Let me put them to the same point. And this I will do to make life simpler. So in general, you can ask, is it a well-defined procedure? So if this is a Whiteman ordered product, does it depend on the order? Is it well-defined? And so here's the result. I will not go you through the derivation, but the claim is that if you start with local operators of spin 1, J1, and J2, and you try to take this coincident limit, it's well-defined and commutative if this J1 plus J2 is larger than J0 plus 1, where J0 is a Regge intercept. Regge intercept in CFT is defined, again, as a high energy limit of the correlator, and you can prove a theorem that in any CFT, this J0 is less than or equals than 1. That follows from the basic axioms. So in practice, what does it mean? It means that if you have two ANAC operators and you put them on top of each other, this corresponds to ANAC operator is an integral of stress tensor. So you plug J1, J2 equal to 2. You plug in this formula. J0 is 1. So 4 is larger than 2. Conclusion that the ANAC operators commute. It looks like might look to you very formal as a statement. Why is it so interesting? But I'll show you that if you try to modify gravity, you will immediately violate that. It's not obvious, but that's what happens. So if you try to modify it without care, with care, of course, you can satisfy that. Take R and add R squared. That's what I call modification of gravity. So compute in a theory which is not just Einstein-Hilbert, but Einstein-Hilbert plus something else.
But something else will be there in any way as mono-variable.
Yes, but you can ask. You might have. You have some, of course, expectation based on effective field theory what you would add to this thing, but there are certain situations where this effective field theory reasoning is more subtle, and the idea is that, let's say you start adding to Einstein gravity high derivative operators with some coefficients in front of them. And so the goal is to understand what are the bounds on these coefficients. How can we bound them from above, for example? How large can modification be? And sometimes there are examples where, based on the naive effective field theory, it looks like, okay, that might be okay, but you can see that it's not okay, and it's related to causality. Yes.
Everything should be practically planned. Okay, as we know.
Oh, of course. Yes.
From whatsoever.
Yeah.
Then what kind of trouble you will get in this case?
Yeah. So the usual troubles that you get is if you do if you consider gravity like standard model and you integrate out electrons, so then you're not in trouble. So this is not applicable. So to these theories, probably I have nothing to say interesting in terms of modification of gravity. But if you try to really modify gravity in terms of adding R square, which did not come from integrating out an electron, then we can talk, and I can tell you that this is not allowed.
So
Yeah.
if you will not add from the very beginning ask you,
Yes.
then your theory will not be renormalizable even. I mean, not gravity, but
Yes.
normal.
Yes.
Quantum field theory will not be renormalizable in
Yes.
form of a graph. Therefore, you have to add it there.
Modified gravity is classical.
Classical, yes, it's classical gravity in the bulk.
Theory of the bulk.
It's a classical theory in the bulk mostly.
You mean now modification of 5 dimensions?
It can, in the end, the idea is that we can do it flat space, but let me not go into this. So, okay, now how do you prove that? Since I don't have much time, let me just tell you very briefly. What you do is that you take, now we have two light rays which coincide, and they integrate it over the cylinder. And so, because the 2 points coincide, you might worry that there are some singularities, and indeed there are OPE singularities, light cone singularities, Regge singularities on the first and the second sheet. You do all the analysis, you derive this. Spare you that. Next question, is there an OPE expansion for these objects? And this question is not obvious, so let me remind you the usual argument for the OPE. We take a vacuum and a radial quantization, we act with a pair of state. We then surround them by a sphere. It's integrated out. It generates some state in the theory. We expand it on the basis of eigenstates of dilatation operators. That's OPE. Done. Now, if you have light ray operators, I told you that if you act with a light ray operator on a vacuum, it annihilates the vacuum. So you cannot run this argument, so there is no such construction, and a priori it's not clear if the OPE exists. There is no Hilbert space interpretation. So nevertheless, we claim that it exists. So what is a claim? This can be true can be stated for any light ray operator. I will just choose ANEC because it's the most famous light ray operator in QFT. So if you take two light ray operators and in the conformal world, putting two operators on top of each other, it's the same in a different frame as putting them in the same null plane. So x plus coordinate 0. Then the claim is that the OPE of two stress tensor, you can write it as a sum of signature plus spin equal 3 operators. Then, because there is this transverse plane y, there are certain representations that can appear in this transverse plane, and I will tell you which ones. And this D is the differential operator, which is also fixed by symmetries. So this is a very explicit formula. And people were sort of thinking about this many years ago, but one of the feelings was that the feeling was that the number of operators that can appear here is so vast and complicated that it's really hopeless to write such a formula. At least that's what I heard from some senior people. But what we will see is that the number of representations in the transverse group is very limited, and the formula is actually very simple in the end. And let me describe, so why is it that we have here spin 2 operators and here only spin 3? This is known as the spin selection rule, and this is related to this coincident limit. Imagine we have two operators in a QFT, and we try to put them at the same point. Usually we don't put operators at the same point because it's an ill-defined procedure, and then we can write the difference to some power and operators of any dimensions. But as I try to argue that for ANX and light ray operators, you can put them at the same point, and then what happens is that you cannot write any distance difference, and just by dimensional analysis, the only operators that can appear here has dimension delta 1 plus delta 2. So this leads to this fact that only spin 3 operators appeared, because it's a coincident limit and this funny kinematics. Then the signature is related to this Rindler reflection. So if you have an integral of a local operator and you act on it with reflection and Hermitian conjugation, it transforms with -1 to the j. And so this is the same, you can formally define this plus-minus signature. And in practice also it's a continuation from even spin and odd spins. And one interesting feature that you see is that if you have a local operator of spin j, its signature is -1 to the j. Therefore, if you look at this formula, we have a spin 3 operator, and if you have an integral of a spin 3 operator, it has to be -1 to the j, which is minus. So that's why also, if you try to do this OPE naively, it will never work, because it's a really non-local operators. You cannot write them as an integral of something. It's a signature plus spin 3. Finally, in these transverse representations, what happens is that the allowed representations in the OPE of integrals of two local guys are inherited from the OPE of O1 and O2. So if you start with two stress tensors, you list all representation in their OPE, you remove the first diagram, and that's allowed representations in SOD minus 2. Okay, so and then you can write celestial blocks. That's how you derive it. I will skip all of that. And one interesting thing, maybe of the derivation is, in a sense, sophisticated harmonic Lorentzian analysis. There is this nice diagrammatic technique which allows you, the manipulations are very hard and explicitly very hard to do, but you can develop diagrammatic technique and prove that, derive formulas like that. And an interesting object that appears in the derivation is a kind of broken transform where you take one operator, you integrate it over light ray, which breaks two other light rays into pieces, and you get some. Presumably, this kind of objects are very important, but in some other context, but it's just appeared naturally. So, and then you can write conformal block expansions. So let me just wrap this derivation up. The idea is that analyticity and spin is very general. It appears in S matrix and QFT and CFT, and these points on rigid trajectories are light ray operators. And So we should understand them. And if you do the S matrix instead of correlators, then this, the analog of a light-ray operator in an S matrix is a shockwave state. Shockwave state is a kind of background, but it's in a sense an on-shell background in some strange sense. And yes, this dynamics of light-ray operators captures interesting Lorentzian dynamics, which are otherwise hard to accept from Euclidean. And so I described you some tools to study them. Now let me describe two applications. First, consider a gravitational shock wave. What is this? It's an exact solution of Einstein theory, which is a Coulomb field of a relativistic particle. That's its form. When a particle propagates through a gravitational shock wave, it experiences a Shapiro time delay. It's the same effect as when you send radio signal to Mars and back. Then the claim is that if you try to modify gravity and you add this high derivative, say, interaction, the non-minimal couplings lead to Shapiro time advances. And if you build, you can try to use these time advances to build a time machine, and in this way to constrain this high derivative operators. And in this paper, there was a qualitative argument that this coupling should be bounded by the gap of higher spin particles. So it's a classical theory, say, in ADS, and so one example of such theory where this is possible is a string theory, whereas this gap is just the string states. Now, one problem in the subject is that is it possible to write a precise formula for this? Because there is a squiggly line because the integral is, the argument is somewhat qualitative. And so the answer is yes, and let me tell you what it is. So consider now particles that propagating through a pair of closely situated shock waves. You can ask, does the result on the propagation of a particle depends on the ordering of shock waves? And in Einstein theory, if you put two shock waves on top of each other, the result does not depend on the order of the shocks. And this is this expression of equivalence principle. Because geodesic doesn't feel the orderings of the shock. However, a non-trivial claim, which was shown in these papers, is that if you add any modification to gravity of the type that affects these 3-point couplings, if you add non-minimal couplings to matter or any other thing like that, then this phenomenon of shock wave commutativity is lost. And so, yeah. Sorry?
You mean that geodesics are different? What is different?
Okay, very good. So
What do you mean by modification of gravity?
okay, my modification of gravity is this. So you add r squared to your action.
So you change the solution?
No, very good. So one famous fact about this geometry is that it's exact solution in any modified. If you add any corrections to Einstein theory, this is still an exact solution because it's a very special killing vector. So the background stays the same in any theory, but what changes is the propagation of a probe particle through this background. Yes, in modified theories, particles do not follow geodesics anymore.
Why?
Because geodesics is just the result of equations of motions from R. If you add R squared, geodesics is geodesics. Yes, yes. So if the theory is non-Einstein Hilbert, particles do not follow geodesics anymore. They follow the equations of motions.
But this has to do with the range for a particle, not for a geometry.
Yes. Sorry, here, you're absolutely right, but here the particle which I'm sending through the shock wave is a graviton itself. Sorry. So, if you modified it, then shocks do not commute anymore, but in ADS CFT, this commutativity of ANAC operators is translated directly to commutativity of shocks. Therefore, if we proven non-perturbatively that this ANACs commute, it should be a principle, at least in any quantum gravity in ADS, the shocks should commute. And then there is an analogous argument which you can run in flat space, which is known from the 60s as superconvergence sum rules. Both of these facts are related to the, if you wish, to causality of high energy behavior of the amplitude. And therefore, we would like to say that there is a general principle of consistency in any gravitational theory, that if your gravitational theory admits a UV completion, then the shocks should commute. And this should be true even in standard model also.
Excuse me, may I ask you a question? You say that this is an effect due to addition of R squared, which has a dimension. So it has to be divided by something like Planck's theory.
Yes.
So are we talking here of corrections of order of the mass 1 over the Planck
So,
mass to some power?
right. So the interesting, you can put here Planck square, and then what I'm saying is not interesting. But if you can try to put something like a string scale, so you can put it below. So imagine a model where there's a Planck scale and an extra scale where this kind of corrections enter. So in this type of model, you can bound this. If it's, yeah, it's and then you can write a precise formula for this A minus C and relate it to the gap. Now, let me finish with talking about this energy correlations. And there, in principle, we can combine this technology with a numerical bootstrap to try to compute event shapes and strongly coupled CFTs like 3D Ising models. So you can write collider experiment in a 3D Ising. And well, we haven't done that yet, but we hope to do it. Another maybe simpler example, and that what probably Grisha will talk about, is that we can do it in n equal 4. And there, this OPE formula predicts that the event shape, you can use some supersymmetry to help you. But the point is that you can write an expression for the 2-point function of energy correlators, and this is a finite coupling formula. So event shapes in n equal 4 should admit this expansion where these coefficients is OPE data of certain operators evaluated at spin equal -1. So you could have asked, okay, what is a spin -1? Can never be physical, but here that's what happens. That the OPE at spin -1 controls this form. And then you can use this formula in practice to make predictions, and I suspect an analogous formula should exist in QCD, but there is a complication due to a beta function, which I don't have time to describe. And well, of course, we check this formula to reproduce known data. But the one interesting plot which I wanted you to show, with which to conclude my talk, is actually the plot was produced for us by Kolya Gromov. And it's related to the small angle behavior of the energy correlator. So imagine you have an event like E plus E minus collision. In QCD, you generate jets. What is a jet? Jet is a collimated flux of energy in localized tubes. The same happens in n equal 4. And in terms of these observables, it's related to the fact when you take two detectors close to each other, they have a singularity. And one famous fact from ADS CFT is that when you go to the strong coupling, jets disappear. So what you can say is that at weak coupling, we have collimated energy flux, but at strong coupling, operators create spherical blobs of energy. And what here we can do is that you can plot this small angle behavior of energy as a function of the coupling due to integrability and technology developed here. And so here, this is a really finite coupling plot. So you start at 0 coupling, where this anomalous dimension is 0, and this thing is very singular. And as you increase coupling, the energy correlator becomes less and less singular, and the coupling around 10, it becomes non-singular, so jets disappear. So in principle, we can start playing the same games in some other CFTs.
Excuse me, I don't understand.
Yeah.
You refer to QCD. In QCD, there is no such thing as strong coupling or weak because
Absolutely,
the
yeah.
coupling runs. It's not true.
Yes.
Conformal field theory.
Absolutely, of course.
Of course. So what do you mean?
So I'm saying that if we do E plus E minus collisions, we will generate jets, and then of course you have a physics. The physics of event shapes has a very simple UV origin, and then all the confinement dynamics, it doesn't change much. If you start with 2 quarks, it becomes 2 jets. Here there is no confinement, of course. So what I'm saying is that in QCD you do not have, of course, these parameters that you can tune. What I'm saying is that imagine you imagine some other quantum field theory which is strongly coupled, and you can ask what happens. How do event shapes look in this tentative quantum field theory? Do we have jets? Don't we have jets? If we don't have Lagrangian, we don't have asymptotic freedom. So what I'm showing you is an example of a QFT where we can answer this question and we can compute explicitly.
You can answer the question in a theory which you don't know.
Yes, if you want a QCD, then this is a more relevant formula. Because if you want to compute event shapes in QCD, and actually that's what people are doing, say Lance Dixon and collaborators, because apparently it's relevant to measuring of alpha S, so people are interested in these observables. And there you can write similar formulas. So this is, if we are talking about practicing QCD, this is a more interesting formula, I would say. Okay, let me conclude. So I try to explain to you some light ray technology, which is becoming one tool in the bootstrap methods, and this allows us to compute new Lorentzian observables. Hopefully we will get some interesting results. And then I just try to briefly sketch a couple of applications. One is kind of holographic in nature, where the ultimate goal is to derive the effective field theories of quantum gravity, which is something which maybe you can have some intuition, but you might hope to derive. And the second is that you can study event shapes and this kind of conformal collider physics. And I think you can generalize it to QCD. I don't have time to describe the details. It's, of course, more complicated to describe these event shapes in strongly coupled QFTs. Thank you.
So if you think of modification of gravity, what is the bottom line? What is allowed, what is not?
Yes, I think what is not allowed is to add operators which are not. So first of all, yes, if you have some quantum matter which you integrate out, like electrons, if you modify gravity through loops, then I have nothing to teach you. It's all standard. If you try to modify gravity classically, which is that there is a Planck scale and there is a nu scale, then I would tell you that it's not a theorem, but from everything we saw, that the only way you can modify gravity classically is string theory. So string theory is like a Higgs mechanism for classical gravity.
So if I'm doing experiments at low energies,
yes,
gravitational experiments,
yes,
and I figure out the deviations from gravity, from Einstein gravity,
yes,
what should I conclude?
you should conclude that you will have extra degrees of freedom, which are higher spin particles. But I think, let me make clear that, say, these couplings, for example, from some experiments, the situation where I'm thinking is that we add this operator at, say, I don't know, 100 or 1000 TeV or 10 to the 15 GeV or some high scale, not like we measure something in solar system experiments. So, and the existing bounds on these parameters are so much weaker than, okay, then I will tell you that if you measure this operator, say in standard model, or if you measure this operator at some new scale, which is not a Planck scale, then you will have to discover that whole tower of higher spin particles at this scale. That's just the claim. If you modify gravity classically, then at these new scales you start seeing many new particles. That's the claim. Yeah. Yes, please.
Given just one operator, I can imagine a situation in which you add infinite.
Of course, absolutely. So you're right. So one operator was in quotes, which means infinitely many. But the important thing is that these experiments, in nature, they're non-local in the sense that they're kind of experiments where you do a scattering at fixed impact parameter. And then at high energies, this thing, it's one beautiful fact about it, it's completely fixed in terms of 3-point couplings of graviton. 3-point coupling of graviton is an on-shell observable, say in flat space, 3-point amplitudes. It's just a set of numbers. You can call them constants of nature. And so all these bounds are on these constants of nature. If you write a specific action with infinitely many operators, you can try to use this action to compute these numbers. What I can tell you is that if you give me these numbers, then there should be degrees, with some scales, then there should be a new degree of freedom at this scale. So it's really an on-shell it's an on-shell observable which does not depend on field redefinitions. And yes, you can add infinite many operators, but what matters is not the precise form of operators, but the value of this on-shell coupling, which is graviton, if you wish, a graviton self-interaction or interaction of matter with graviton. So that's what.
May I disagree with you?
Please,
Because all what that you said is only valid if the underlying matter theory is conformal. We know, right, because you use this, the very definition of this A and C only refers to the conformal field theory, right? The scaling of the free-point function is power-like with certain anomalous dimension only in the conformal field theory.
Yeah.
If the theory is not conformal, and our nature is definitely not conformal, we know it for certain. All scaling, I mean, everything falls off exponentially at large distances, right?
But
His logic is different. He takes some gravity theory,
yes.
adds cosmology at once. It says, antideceiver, so at the boundary there should be some CFT. Antideceiver, yes. And that auxiliary CFT for that gravity effect of Lagrange has some constraints on it.
Actually, there is even a simpler thing. All I said can be repeated in flat space with massive particles. An important exception to what you said, that things decay exponentially, is the exchange of a graviton. And all I'm saying is about the interaction with gravity.
Okay, you are considering a gravity in a certain background.
It's a...
And matter doesn't count, right? Because at large distances, all matter is massive. You integrate them out,
Yes,
and
yes,
they
yes,
only
yes, yes, yes.
change a little bit the coupling
Yes,
constants,
yes.
and then you study the
Yes,
behavior.
yes, yes.
So this is an auxiliary trick in a sense.
Yeah, so...
It's conformal field theory.
Yeah, so let me clarify. So one problem, ancient problem, which I don't know, maybe you know the solution, but in flat space as matrix theories, there are no rigorous bounds on the Regge limit in gravity. And all CFT buys you is a rigorous limit on the gravitational Regge limit. So CFT is only needed to derive these bounds rigorously. In flat space, plausible, but you do not have this, non-perturbative tool, but otherwise you can do it in flat space.
When you speak
Yeah.
of the tower of particles,
Yes.
you don't mean matter particles, right? What do you mean? You mean a large number of gravitons or what?
No, more precisely what should happen is that you have Regge trajectories. So
Regge trajectories for what? Or of what?
of matter, it's matter. It's matter part. It's extra states. It's extra matter particles.
States of what? No, because all you do is only for massless particles.
No. It's not.
If they're massive, there is nothing.
Yes. So
Because all correlators fall off.
Let me clarify. So consider a scattering, say, of two gravitons. Yeah. So you have this Shapiro time advance, for example, and then you discover that at some scale, you say you decrease the impact parameter. Sorry?
You mean by scale, some scale?
Oh, yeah. So let's consider scattering of two gravitons and impact parameter with a scale B. Okay. It's very large energies. It's dominated by GR. Say, because all these high derivative corrections, they decay. You start bringing these things together, you can show that as soon as your impact parameter becomes of order of this alpha Gauss-Bonnet, you start producing time advance. So at this point, the distance can be already small enough that you start seeing an exchange by infinite number of high spin particles. And the fact that they decay exponentially will not save you. And the claim is that your effective field theory should get modified. And at this point, this problem will be solved. So that's the spirit of the argument. That's why this high derivative correction is related to the mass scale of new particles.
In the case that the scale doesn't exist, everything is at the Planck scale.
Sorry?
If everything is
at the moment we cannot say anything non-trivial, because what happens is that if let's integrate an electron loop. Say it generates this non-minimal coupling. So a priori you would say, okay, I'm doing scattering at impact parameter 1 over mass of electron. I will start violating this thing, but as soon as you at such a small impact parameter, you will find that there is a loop of electrons, and this computation will break down, and the whole thing will be consistent. So I have nothing to say.
Yeah, but this is one particle, right?
Yes, but that's so. Let me resolve this puzzle. So the claim is that here the effect is quantum, And in a quantum theory, if you have a box, you exchange two particles, one loop. But by exchange of quantum two particles, you can think of this by exchanging a classical of particles of many spins because they can be in many partial waves. So that's, imagine you have a pair of electrons, you can decompose them in any spin. So if you want to think of a pair of electrons as a set of classical particles, they have all spins. And so here what happens is that since I'm thinking of the theory as classical, so I'm not allowed for loop diagrams. So we should take this box and try to think of this as many exchanges. And if we do that, we will discover that it's like having the whole tower. And so again, the best example where we can really write explicit amplitudes and show everything is string theory. And there's this exchanges, just these high spin resonances, high spin excitations of the string. So that's the picture. So quantum versus classical is important here.
Yeah, but that's you really insisting that these high resolutions are resolved at 3 levels. Yes.
Of course, yes. As I said, if you resolve them quantum mechanically. But actually, I couldn't find the computation of these observables in standard model.